Okay. So I'll make a start because there's quite a bit of stuff to go through with this course, as I'm pretty sure you're all aware. The exam, when you're first looking at it, makes no sense and you have no idea how it's relevant to the course, because the questions, other than question one, really are very different from your assignment question. However, when you go through and look at past papers, you'll notice one thing: they are all essentially the same, which is great. So in my opinion, the best way to study for this course is just do past papers. You'll notice year to year to year, they're all the same. It's the same layout. So as you can see here, we have 3 questions. Pretty much just go through each question. It's the same process. So your first question is going to be a column rafter question. So that's going to be a basic portal frame design from assignment 3. And then you have an end plate connection picture, pretty much the same thing every semester. And then a bulk capacity and welded end plate connection design. It's simplified from what you would have done in steel design with Kitty and Mullock, pretty much because you don't have that much time in this exam. The second question is going to be a retaining wall design. The only thing that changes in this question is your geometry, but again, the process is exactly the same year after year after year. And then you're going to have a deflected shape question. This question I find is the hardest question in the exam. The only way to study it is to practice. I'll show you when we get to the question, but it's probably the most unseen question in this exam. Then your third question is this shear force of a steel member, and then you're calculating your bending moment and member size capacity, and then it's another connection drawing. Again, I think it's always the exact same connection, so you just take them into the exam and rewrite it. Overall, this is another one of the exams that you're probably not going to like in terms of it is time pressured. There is ways you can get around to make your most marks in this exam, or doing less. You're not going to get full marks if you do it certain ways, but it's small cheats that allow you to get things done faster. So I'm going to go through 2020, 2019, and 2018 exams if I have time. Please be aware my work solutions are rushed. There are errors. I'm aware there are errors, especially in the 2019 solutions, because last year I wrote these solutions in 2 hours at the same time as I was doing 2018. So I did 2 exams in the time you meant to do 1. Not my smartest idea, but it is what it is. So with the 2020 exam, this wasn't my exam. I did 2019, but it's essentially the same. So this first question starts off as a portal frame. So Ron likes to make a story with this question. If you read them, it goes from the TARDIS to somewhere on the moon. Enjoy it. It gives you a good laugh in the exam. I should check if they can hear me. So the first question is essentially working out. So the first question is essentially working out the capacity of a steel member. It's always going to be the same thing. You just got different loads and different geometry. So in this case, as you can see, I highlight all my important information. Probably used to me saying that if I've tutored you for a few years now. But it's the best way to like go through and pick out the important information, especially when you have a big paragraph which is mainly just a story. So from this, we're looking at, we've got this, we're internally pressurized building. He says that it's similar to wind design in AS1170. That's important to notice, because when you're going through, you're going to have to look at your loading combinations. And he said it's equal to WU. So essentially, this is our internal wind pressure. Then we're looking at our size, so it's an 800 WB. So make sure you have one seal in the exam. You'll pretty much not pass this exam without one seal. You need your capacities throughout this. You've got your geometry. One weird thing about this one is he's on the moon, so make sure that you look at lunar gravity versus Earth gravity. You can also assume that G equals 10 to simplify things in this subject. It just makes things quicker. He's also saying that there's no atmosphere or wind on the moon. Therefore, you only have to look at that internalized wind pressure and no external pressure on the building. We're looking at structural adequacy. We're in a portal frame, and then we have to look at a suspended mass. So this is from the center of it. So what I go through and did was I wrote up my geometry, wrote all my notes from his paragraph so that I can refer to that pretty instantly. Then I had a look at my loading combinations. These are from 1170.0. Make sure you have a look at all of them and make sure you actually do them, because people will forget and just do one load, whereas you need to have a look at all of them. Then the best way I find is to go through and break up all the loading cases. So I go through my dead load, my superimposed dead load, and then all my live loading and wind loadings. So I started with my dead load from the 800 WD. This is a nice simple approximate analysis question. And you just get your maximum moments. One thing I will say is if you're under pressure, don't worry about trying to find the exact hinge location, just assume 0.2 L. That's what I did. It's just essentially a waste of time trying to get the exact hinge location. You're going to be under time pressure. So that gives me my unfactored dead load for just this member. I then go through and have a look at my superimposed dead load. So he says there's a 500 kilograms per meter squared load from the cladding and the mass. So you need to look at that per unit width. We've got a 2 meter loaded width as 2 meter spacings. So that's 100 kilograms per meter, approximately 1.66 kilonewtons per meter. That's accounting for the fact that we're dealing with lunar gravity, not Earth gravity. Therefore, go through again and find your loading thing. And then the next thing is probably the trickiest part of this question, and it's dealing with this wind or air pressure due to that internal pressure coming out of the ground. So as you can see, we're essentially dealing with shape like this. We've got 50 kPa. This is a rather large force, which equates to 100 kilonewtons per meter. I break this down into our force on the one column each, and then the force on the beam at the top. And first thing I always do is do your beam at the top, because that's your simplified method that you've already done 2 previous times for your dead load, which creates this. And then we essentially have these 2 column loads. They essentially cancel each other out, which is really, really good when you're under time pressure. So I wouldn't even bother going through and calculating your moments due to this internal pressure on your 2 columns. It's just a waste of time. However, I wanted to do it to show you that they are the same. So we've got 625 on both sides in opposite reactions. And then we're looking at our live load. This is something that's often forgotten, and in this question, unless it's specifically said, and you have to take your live load from 1170.2. It's an imposed roof load. It essentially comes out as 0.5 kilonewtons per meter. This is in comparison to your 100 kilonewtons per meter from this wind load we have. So therefore, it's not critical. One way to get extra marks is to say that it's not critical, and you don't need to actually do any further analysis on it. The next thing we're looking at is a single mass. It is assumed to be a superimposed dead load. Once again, you just use approximate analysis to get your maximum moment. So we're using an unknown factor X, and that essentially goes through and you work this out. Through inspection, you can already tell that 1.2G plus that wind load is going to be your worst case. This is because this wind load is so much larger than any other load in our system. So 1.35G is not going to go at any time. Therefore, we're going to have a look at this load case and our capacity. For this question, I would just assume full lateral restraint. You're going to go through and calculate something later that doesn't assume full lateral restraint. Plus it's on a portal frame, which also has all your purlins, skirts, and fly bracing to make it essentially full lateral. Calculate your MS, which is FY30X. You have your member size, so you take your ZEX and FY out of one steel. Make sure that you're using FY for your flange, because moment is taking the flange. If you notice there's differences between your FY and flange and your web, this calculates your phi. It's half of that sentence. That should say times 2,256.8. Did tell you I rushed this. Therefore, go through and calculate what your maximum moment could be, just superimposing all your loads together. This will give you essentially a mass of 1,200 kilonewtons. I then just confirm that without its left shape. Does that make sense? It's essentially every question is the exact same. It's just different loading arrangements and different geometry of the portal frame, but the exact process is followed in every question. I wouldn't use my numerical solutions as full work solutions because I'm pretty sure there are some calculation errors in this. I did this very quickly last night. But use these as processes to follow. The next question is a bolted ridge plate end connection between a column and a rafter to achieve full moment capacity. So when you're having to achieve full moment capacity, that means you need to connect the flanges. Whereas if you were just dealing with a hinged board or something that's not a full moment, then you wouldn't have to connect your flanges and you only connect your web. So this is essentially the sketch of this. I believe I gave it to you last semester as well. Take a photo of this. I can't actually give you any of these work solutions. But take photos of this at the end. You can come and take screenshots of my sketches if you want. Things that I would notice and things that I was told from the person who ran my tutorial back 2 years ago, try to put in these double plates because of the massive size of our members. So we're dealing with an 800 WB. That is massive. When I've been designing stuff at work, we're typically dealing with a 300 UB, not a WB. So you can see just how much larger these connections are. So you want this extra strength, which is also the reason why we have this shear sticker in there to increase our shear strength of our column. Make sure you have the bolts in the flange, which transfer all of our loading, and then also our web weld onto our end plate, which is then bolted into our connection. Anyone has any questions about this connection, let me know, but it's what I was shown, and I've just transferred that through for the last couple of years and seems to be what's correct. Now, this bolted end plate connection. The process that I followed for this question is the process that I was shown for this question back when I took this course in 2019, and he learned it from the person who taught him this course, and it's just flowed on through. It's a simplified design method that you essentially will get you the close enough answer. So we're finding out eccentricity of our bolts. So we're looking at our connection, our impact connection that we've drawn above. So we've got our eccentricity. So we've got our depth of our member, our thickness of our flange over 2. Essentially, that there. Then we're calculating our tensile force of the whole member. So we're having to look at our full member capacity because that's what we've designed our structure to. And that's over 2 times our eccentricity, which gives us our maximum tensile force in our bolts. In this case, I have used 5 M36 bolts. That's what I chose to use. And you can see my bolt arrangement off to the side. I would highly recommend showing your bolt arrangement because depending on your member, it will depend on your number of bolts. And that gives us our capacity. To find capacities of bolts, you were given a table in, I think it's header 6 or 7 that gives you bolt capacities. Use that. Bring that into the exam. You do not want to be sitting there trying to calculate the tensile capacity of the bolt or a plate in the exam. You've got given them, that's what we use in industry. Please bring that into the exam. So therefore, we need 5 M6s at each flange. The next question is the one where not 100% certain of the methodology behind this, but we're going with it. So we have a 12mm continuous fillet weld. We need to have a look at how it connects to our tension flange. So what we're assuming here is all of our tension is taken in the top flange. So we have our maximum tensile force of 2,577 kilonewtons. We also have our length of our weld. So that's the length of it if it was welded on just this top flange here. In reality, you could weld some of your web as well, and that would take capacity. So that's just a formula you're given. Use it. It's easier than trying to work it out yourself in the middle of the exam. And therefore, we're given 3.99 kilonewtons per millimeter. When we're dealing with a 12mm continuous fillet weld, it has a maximum capacity of about 1.9 kilonewtons per millimeter. Therefore, we need a larger weld size. Again, that capacity is given in your bolt and weld capacity guide in that handout. Really, really useful handout, especially next year as well. So we're going to need a stronger connection, and then we're finding our plate. So we have our capacity we need to hold 3.9 kilonewtons per millimeter. This is our formula for the tensile force of the plate. FYI, BI times TI squared over AFE. AFE is a formula given. We're going to assume an AF value of 65 millimeters. Don't ask me why we've assumed that value. It's given somewhere. You can change the value around. However, it's easier just to go with the straight out 65 that I've essentially got here and have been told in the past. And then we can calculate our AFE is equal to approximately 47 millimeters here. We're using 36 bolts. In other examples, we use M30s. It really just depends on what our bolt size is. Then we have a look at our flange width. So we have BF plus 20. BF is given in 1 steel, add 20, so it's 320. So we try a 40 millimeter plate that gives us 2,745 kilonewtons. Gives us sufficient capacity. Also check your minimum distances. You don't have time, you don't have to calculate them, but write that down that you have to check these minimum and maximum distances. It's another way just to get these bonus points. That's essentially question 1. It is the exact same in every year. You literally just plug and play with different numbers. Does anyone have any particular questions behind question 1? Yes.
So the part where you talk about the different load cases, and you said that this is not going to be a critical case, was the thing that you just wrote down sufficient?
So if from inspection you can tell that it's not going to be critical, that's all you have to write. If you're uncomfortable making that assumption, write that, calculate both, and then show why one's bigger than the other. But if from inspection you can tell that, when you're dealing with a live load of 0.5 kilograms versus 100 kilograms, you can tell straight away that one is going to be greater than the other.
We just do 1.35G.
Yeah.
1.2.
Yeah.
1.2G.
Yeah, so that's all you really have to do, but you have to say why you chose not to use that load case. Using the latest versions of AS4100 and 1170.2, what did you use in this course?
Whatever you want to use, I think.
Whatever you would prefer is my recommendation. Whatever you're more comfortable with. There's no point learning a new code for this. Especially if you guys don't learn AS3600, whatever the previous code was. You don't need it. In industry now, we're using the new steel code. The new wind code hasn't come into BCA yet, so we're allowed to use the old wind code.
Run live for 2021 one though, because he says it's not like practice yet.
It's not. It's not.
Yes.
So if you're used to the new wind code, go ahead. If you haven't had any experience with it, I really recommend using it. There's a couple of factors that have changed, like the climate change factor. Yep.
Just by looking at that, we don't actually need to take the codes into the exam.
For this question, no. I would bring in 1170. Definitely those steel.
The tables we've got in the handouts you bring in, obviously.
Yeah, look, you can get away with just using the handouts.
Cool.
I personally like having the codes just in case. The only thing that's probably, there's a bit in question 2 that needs 3600, but as long as you have everything noted down, you should be fine. And then there's a bit in question 3 that uses 4100. So in 4100, we actually, in question 3, we actually calculate our member and our member capacity, which needs those alpha S and alpha M factors, which I'm used to using the code, so I just flip through the codes. But if you have everything you need,
It's fine.
it's fine. Just make sure you have this. So make sure you have one seal. You will need it.
I think that's in one of the handouts, but yeah.
Yeah, I think it is one of the handouts. I haven't looked through the handouts in a while. So
I'll be like an exam survival handout. I think it has, I'll look an exam survival handout, which I think it has all of the sheets you need.
bring that in there.
Yeah.
Look, I bring everything in. My opinion is you're better to have it, not need it, than need to not have it. You can see this is my concrete code. This is the 2018, so I only started using this last year. You can see all my little tags on it. I'd rather just have it. So like,
yeah.
And then I have like little things, so it's like I don't actually have to read tables sometimes. It just tells me what I need. That's just coming from a,
yeah.
I don't like to miss things if I know that I know where it is, but don't have it on me. So question 2, essentially a retaining wall design. So this is going to your assignment 2. That was the retaining wall design. So you change the geometry area. It is essentially, you can see here. This is my one. I wanted to put it at an angle. I don't like that idea. Different geometry. exact same question. If you have a look, the wording for the question below the geometry is exactly the same. So what we're doing for this question is we're calculating our height. So we need to calculate this height here. And then I just realized that I assumed something wrong. Good job, me. And then he's given us a 15 kPa light load factor as well as a different dimensions. We have N32s at 300. Pretty sure he always uses N32s. Really nice. But essentially the process is the exact same. So what we're going to do for this is we're going to calculate our maximum moment and maximum shear at our critical location. So our critical location is essentially this spot here, which is here, because that's where our maximum moment in the stem is going to be with the minimum thickness. So we go through and calculate all our different forces. So we have water with this. So we're on the side of a concrete water storage tank. One of the most annoying parts of this question is trying to work out where the water is.
Yeah.
Because he never actually tells you. It's on the side where he has written the reinforcement. I have learned that. So it's here. I can also tell you it's here just from experience designing water retaining structures. Wherever your slab is, it's going to retain water. Don't stress about that in your exam. If you assume the water on the wrong side, it's not critical. It's just annoying. So what we're going to do is we're going to determine capacity at that section. So we're using simple concrete design. Tension equals compression. Compression equals alpha 2 F CV KUD. Always assume under reinforced. Always assume that phi equals 0.85. So we calculate our area of steel. We have our steel. It's given. Essentially, we calculate our tensile force, which is 1,333 kilonewtons. We can calculate our cover, our depth to our reinforcement, so D minus cover minus half dB. When it comes to your classifications, we're using from AS 3600, a B1 classification is of holding fresh water. Just assume that. That gives you a 30 ml cover and an F-C of 32 MPa. I haven't actually done that in previous questions of iterations of my solutions, but I just wanted to write it in there. This time to make sure you guys are aware that that will also give you extra marks because you do need to know your classifications. Calculate your KUD. That gives us essentially 0.1, which confirms it's under reinforced and phi equals 0.85. And then you can calculate your maximum moment. Because it's that part of the question is pretty easy. You should be able to do it without much thought. It's pretty simple moment design. So then we're doing our actual design moment of the thing. So I like to break it down into the simplest forms possible. So we have our live load, which is a 15 kPa force. We have our water load, which is that triangular load here. Then I've actually split up our live load into two sections, F1 and F2. That's just due to our capacity, our unknown here. So we have an unknown of this. I just realized that I calculated the unknown. Yeah. And not to the top. So it's 300 plus whatever I calculated. Good job, me. Read the question. So just calculate essentially your forces. So we have force 1, force 2, FQ, and FW. Always just assume gamma of concrete is 24 kilonewton per meter squared, and gamma of water is 10. Simplifies things, you don't want to be dealing with annoying decimal points in the exam. We're taking moment around this point here. So essentially for all three of these, we're doing to the center line of it, which is 300 mil. And then for water, we're dealing with a triangular thing, so it's half the height, it's third of the height, so it comes in there. So I calculate both my forces and my lever arm separately. That just makes it easier later on. A note, technically water has a capacity factor of 1, not 1.5. I don't actually know where that comes from, but it is a thing that I have designed to. That's just a note. And then calculate the sum of your moments. So calculate the sum of your moments that we've got. So we've got all our design loads. And then we have our max moment of 598 meters. Make sure you include your load capacity, your load combination factor, so you can see where I've included 1.2 and 1.5 here, which gives us a height of 6.5 meters, which is that height. Should be that height. Yes.
Would it be insane to, because it's a live load, it could go on like half the slab, so you could take the worst case live load?
Yes, so that is true. When it comes to road designs, it changes. So in this subject, in this exam, I wouldn't bother.
That's all I need to hear.
I would just assume it over the entire length and do everything per meter width. But technically, when you're dealing with roadway design, you have like 3 different locations that you have to check across. I wouldn't really bother in this case. You can, it would be critical if you just had it on like this half. Write it, note it down. But you don't really have time to think that in depth. And then the next thing is check shear. Make sure you're using it to the right code. This is to 2018. Sorry, I'm used to using both the 2009 and 2018, and sometimes messes with my head. So we're calculating our maximum shear. So we have 3 loads going down, 1 load that's going to give us a shear force. So the only shear force we're going to be getting is from FW, our water, which is 5x squared, because that just makes it easier instead of having to go from calculating our shear. Because in this case we're assuming no shear reinforcement, KV equals 0.1, but that will change because, as you can see in this case, shear reinforcement is required. My note about that 1.5 versus 1 is surrounding this, because in water, with the 1 load factor, it actually works. And then when you put the 1.5 load combination factor, fails. And then our thickness of the base plate is essentially just going to draw anchorage of our 32 and 32 steel. That's the only reason we have the thickness there. So you just calculate your anchorage, it's half of that, because we can use either a hog or a hook, hook or a cog. K1 equals 1.3, as we've got more than 300 mil below the steel. K2 equals 1 when PV equals 32. If my assumption is correct, that it always is 32. You can always just assume that. However, I have written the formula of K2 next to it. And then K3 is approximately equal to 1. That gives us our anchorage length. And then our minimum thickness is half of that length plus that cover. So it's approximately 950 millimeters we need. Yeah. Does that all make sense for that question? Next to my least favorite question in the event. So this question here.
Oh, sorry, with the base one there, why wouldn't we have to worry about the moment capacity?
Because you've already got the moment of, you already got the capacity here.
Yeah. Oh, and because
And
we
it's
say
gonna
it
be
needs to
thicker.
be thicker, it's all good.
Yeah.
Yeah.
So this question, this 2020 first example, isn't the best one to give you. As you can see, not stable. Reason why I can work that out is, so we've got this hinge here, which means that we cannot have any moment at this point. So if we're just looking at this section of our frame, we can't have any moment here, which means we can't have any moment, we can't have any vertical reaction force at support 2. Because if we had a vertical reaction support 2, we would have a moment essentially going as the lever arm increases. We also can't have a horizontal reaction at support 2 because that would create a moment in column 2, and because it's a fixed frame, it would induce a moment into beam 2. Which means that essentially beam 2 and column 2 have no forces, no loads through them. Our next thing is we're looking at B1, and so our B1, which is our beam and our column, because we've got no loading in support 1, we can't actually have any horizontal load support 1. And if you know anything from first year structures, if we've got no load in here and we've only got a pin support, it's not stable. Now to confirm that, it's definitely not a stable structure. So what I actually believe he was meant to do is something like the 2018 exam where you have pins in this location here, which allows you to have continuous moment. So we've essentially only got a reaction force at support 1 and no horizontal. It's not a stable structure.
What did you do then?
I don't know, because this wasn't my exam. I would just say it's not stable, and it's not.
Easy 10 marks.
Yeah. If he does something like this again, that begins in column 1. Does that work? I don't believe it happens. Like I'm checking in space now as well, and they're just saying it's stable.
He wants you to do that, right?
Yeah.
Say B2.
Yes, that's
So
Yeah, I think it's
So this question would have been nice last year. But I thought it was the hardest in the exam. Because it's not so my key tips for this is like they require practice, just make up little frames and space cuts and practice them. Or the easiest way to practice, or like if you're looking at past papers and trying to work out or assumptions are correct, put them in space out, review any tables and reaction forces. And yeah, so it's practice is the only way to put this question. I don't like it. It was the most stressful question. Make sure that you remember that at a hinge your moment is 0. And then just think about, so say, again, we're using this one, if we've got no moment here, we can't have a moment here. Which means we can't have any reaction forces here. We can only have repetitive here. If we were looking at just being 1, you know, it would want to create a bending moment. Yeah, but we've got no vertical, we've got no horizontal reaction force at support 1. Make that moment. It would would just be coming up like that, and then it's got nowhere to go, so therefore that's why it's not stable. I just copied this across just so I could go through it easier. In 2018, you can see that they've slightly shifted this in, so going to where it's in column 1 instead of being 2, which means that you can't have any moment across this member here. Which means that there's no reaction force at the support in the horizontal direction, which means that you can't have any horizontal reaction in your other support, which means there's no movement across either of these, and therefore you also get a shear force within your column. When we're dealing with our moment, sorry about that, so linear from a point load, and then because we've also got this vertical reaction force here, it counterbalances, and we just got moment along our top beam member. And our moments in our columns, and then our shear force is just using our reaction forces that we have PL and then our two vertical responses. Does that make sense? It took me a little while to try and wrap my head around what to do with these questions, but if you can follow working backwards from the hinge, it's always an easy way, and then out of like good shape. It's hard to assume exactly what happens, just remember that the easiest way to work out these are quantum shapes. Does that make sense with this question? Question 3, it's one of the I think other than 1 year you had them on an angle, it looks the same. If you have a look, like that's a different question, but they look very similar. It's the depth of the slab, that's about it. So essentially we have this steel frame, and we construct a slab on top of it. We have a 150 mm thick slab, which is supported by these steel members. We have a 5 kPa imposed load, so that's our live load, and two 2.5 ton movable point load. It's going to occur anywhere on the floor. So, question A is for beam D. So these beams here. What is our maximum design shear force? So we're dealing with 1.2 G plus 1.5 Q. So like you take 5 kPa, which turns into 30 kilonewtons per meter when you're using that 1.5. So combination factor, then we have two 2.5 ton point loads, which are essentially 25 kilonewtons each. It's 37.5 kilonewtons when you're applying that 1.5 live load. G is 100 kilograms per meter, which is 1 kilonewton per meter. And then our concrete, so we're just essentially finding the force of our concrete, 150 mm thick, so 0.15 times our width times our density of concrete. They are, so other than your point loads, they are applied as all UDLs, which comes out, so it comes out as about 48.5 kilonewtons per meter over your length of D, which is 12 meters, which you can calculate as 291 kilonewtons, and plus your 2 point loads. So the maximum shear force is going to be if both point loads are located essentially over the support at the same point. So it's 366 kilonewtons. Pretty straightforward question. Just making sure that you apply both point loads at the same location if you have them at 2 different locations. Essentially, not as great as if they're at the same place. So then for part 2, we're calculating how design bending moment of our beam B, which is beam along here. So assume everything's one-way spanning, so all of the mass of the concrete goes onto our D beam and our E beam, not anything onto B. So we essentially have 3 point loads. have D is 291 kilograms and E is 45 kilograms. That, because it's half the length, it's half the shear force. So we use superposition to find our moment of these three, which comes out to be approximately 2,036 kilonewtons. So in this question, our maximum bending moment isn't at the center. However, unless you want to go through and calculate it exactly, it's easy enough to just say, and it is close to the center. So just calculate it at the center. If you have time, you can go and calculate it exactly. And then calculating your bending moment due to the dead load of the beam itself. So we were told that it's assume 100 kilograms per meter. So that's what we've done. And then put your point loads at the center, which gives us our end star value of 2,000. 5.9, calculate a section. So probably the best thing to do here is we don't have full axial restraint, so we can't just use our section capacity, we have to use our member capacity. So to find the approximate member to start with, dividing everything by 1.5 will give you an approximation of the member size you should use. So this is probably the most critical takeaway from this question. So we need to find a member that approximately has an MS of 3,707 kilonewtons. Assume our Fy is 280 MPa. That's just because when we're dealing with these large sections, that's typically our flange Fy. Therefore, the ADX is approximately 13,000. So I just chose a section out of one steel that had that ZEX. And I used 100 WB 296, which had this as our ZEX and our XY as 280 MPa, which gives us a IMS of 3,730 kilonewton meters. If you have time, and I would highly recommend it, go through and calculate your member capacity. So MB is alpha S, alpha M times NS. Alpha M, again, have time, calculate it using this formula properly. It's always approximately 1.3 with this question. But that is the true formula for it, and that is how it is calculated. So it's using the midpoint, your maximum moment, and then your 2 quarter points. And then that's to give you alpha M. And to get alpha S, you have to go through and calculate my favorite question from steel, which doesn't actually fit in our calculators. So we calculate our our effective length, which is KT, KL, KRL. KT is always 1, KR is 1, and KL is 1.4. So just assume all our masses on our top flange, because that's where it's all applied to. Insert that into this masses equation, which gives 6,230 kilonewton meters, and then use that to calculate alpha S, which comes out as 0.714. Then when inserting that all back into this original equation, we have that should say phi MB is 3,315.7 meters. Again, another important point with this question is, if your chosen section is too small, just state, choose a larger section. You do not have to go through and calculate all of this. Again, it's a waste of time. Just say, try this. You've already demonstrated you know how to calculate it. And then our last question from this exam is sketch connection from B to B that conforms with the assumption, showing everything. Always this. So we're assuming no moment transfer, so therefore we don't have our flanges connected. We have a larger member. There is another beam on the other side, that's why that is there, I just don't have room for it. Make sure you show your welds and your bolts. This is a clear plate. And that well also shows that we've got lateral restraint as critical flange, which is why we can use that effective length of 4 meters instead of the full 16 meters. That's essentially the exam. If you look through 2019 and 2018, you'll find that they're essentially the same thing, slightly different arrangements. Same process. It's an easy exam to pass if you practice. It's a hard exam to do well in just due to the sheer volume of work that needs to be done in this exam. Does anyone have anything in particular they want me to go through? Yes.
Are there any other connections, or is it just those two?
I have sketches drawn up of possible other ones he's given in the past. So I've looked at sketches back to 2016. So you have the beam to column. It's always one of these ones. So you have a beam to column connection, a rafter to column connection, and a rafter to rafter connection. That's for question 1. And then the question 3 is always the same. So it's always that one. So if you want to take photos of these, take photos of these. If you want to come up at the end, you can take photos from your computer. I just can't send them to you. Ron has expressed his wishes multiple times to not actually send them out.
It's free to my mom.
Well, question 1A, what are they actually asking us to do? They're saying like with these maps is suspended to like stop the bending movement. What actually is that? Like that last paragraph.
Wait, how do you not know? Practically American to me. He plays good.
Friday, like my feeling.
Julie gonna call you or?
So it's like friends that have decision.
Depending on.
So we're trying to find an adequate member for that. So that's what that 1.5 information of how much it's going to be reduced by. So it's always approximately 75% depending on how many you use. Yeah, it just gives you
When you get your member selection, it doesn't need to match that.
no, it doesn't have to match. It's just an approximate.
Yes, so that was to get the original member, but we only
Yeah. And or Johnson, I'll call you Andy, not your name. And then thank you.
No, you can't. Don't let him do it. Don't let him do it.
Yeah, I know, right? As soon as you said, I just went over that.
Everything's on the line.
Something's wrong with.
Oh, okay. Fingers crossed.
Yeah, exactly.
I'm like the final this That's what I got. Anyone have any other things you want me to go through?
Yeah, just assume that it's one.
Do you know anyone?
JJ.
If you don't have time, assume.
So you haven't uploaded, or if you haven't done the steps, I'm not.
Yeah, no,
that's it.
I knew it was supposed to be that way.
Well, no, that's something else. This was something.
Better off being something down and writing, don't have time.
How did she get paid?
Well, you just let me know which it is. But these are one of the things that like.
Like not actually gonna
Oh,
start.
that's why I haven't tried notes.
I sent you screenshots. Oh, you can't. But you
Right in front of my.
And it's 30 bucks an hour. Do you want to do another talk or? Let's go. Charlie. Yell out. Hey! Cheers.
So if no one has any particular questions that they want me to go through, I'm going to go through the 2019 exam. Still aware my numbers are wrong. I am aware you don't need to point them out every time. You'll quickly notice in question 1 how wrong my numbers are. Don't rush. And read the questions. 2 very, very critical things. So if we're having a look, question 1, when we're running through this question, you see another lovely story. This time we were just UQ management, not as exciting as being on the moon. 2018, you're in Gulliver's Travels. I feel like I missed out. So we've given a pin-based portal frame with 10-meter centers that span 40 meters with 10-meter high columns on each side, and we're using 1000 WB 215s. That is fully laterally braced. We're doing self-weight of 0.4 kPa, which doesn't include the weight of the portal frame. And then we've got a uniformly distributed load over 1/2 of the rafter and a mid-span point load of 100 kilonewtons. So these loads do not have to be added in combination with wind loading. That's just something he wrote. He'll pretty much tell you exactly what he wants every year. Pretty much just means you don't have to calculate wind, which is great. Wind is time consuming. It's probably all aware, and you will become more aware next year in design 1. But very, very similar to 2020's exam. We've got a portal frame that is 10 meters high, 40 meters span, and 10-meter width between each member. So we have our 2 loading combinations of 1.35G, 1.2G plus 1.5Q. So we have a superimposed dead load of 40 kilonewtons per meter. So we've got 40 kPa. That is wrong math. It should be 4 kilonewtons per meter because 0.4 times 10 is not 40. This is the start of why I'm telling you don't use these solutions. And then we've got 100 WB 215. This is another great mathematical error of why you don't do math at 12 p.m. At 12 a.m. 250 kilograms per meter. It's not equal to is not equal to 21.5 kilonewtons per meter, it's 2.15 kilonewtons per meter. So we're off by a lot. Please ignore that. Massive mistake. So I got 4,428 kilonewton meters. It's like 448 kilonewton meters. And 700 instead of 7,000. Process is the same, just make sure your factors are right. But essentially it's the same thing. You get your orders, you've got your UDL across, simply support member, and then a fixed support to the end. And then we have our live loading. So we have a 10 kilonewton per meter uniformly distributed load that stands halfway across, and then we have a point load of 100 kilonewtons. So that's what this essentially is. So you break this up into two components. You have your 100 kilonewtons point load, which essentially has a distributed moment like this. And then we have our half moment like this. Probably the most confusing thing among them was trying to work out what that is and what it was. Worked it out in the end. Approximate shape like this. So if you have your bending moment charts, it is in one of them. Not sure which one. Again, I just always assume that in the same location of point through L. It's just easier than trying to work out the actual use location. You can use 0.1L, 0.5L. It's approximate. It works out in the end. If you've got your bending moment chart that has this in it, use it. If one semester, if not, you have one from structural analysis last semester, take them into the exam. They're really helpful. I did it, would have liked it. So then we use principles of superposition and quickly realize that my factors are way off. Yes, ignore that. Therefore, determine your capacity. So we're told in this question that it is full lateral restraint. It will always be full lateral restraint in question 1. So it's just again MS equals FYZEX. It's approximately 3,800 kilonewton meters capacity, and that by 0.9. It's not sufficient in the case of I can't math. It was actually sufficient in the actual question. That's why I don't really want to do that question in detail. Yes.
So say we make that mistake in the exam, what do we do? So like we just,
Acknowledge it.
okay, right.
You probably won't have time to redo it. So say if I did that in my exam, I look back when I'm reviewing, I've got 10 minutes left. Oh no, I don't have the time to do this. Acknowledge it. Say, I have made this mistake. I am aware of this mistake. For example, up here, where I first made the initial mistake of having very wrong kilonewtons per meter, and if you have time to say that's not 40, that is 4, acknowledge that. But if you don't have time to go through and do the whole process again, just acknowledge at each point you've made the mistake. I know, probably I told you this before, in my concrete exam, back when I was a little second year in 2017, so I think in the ages, I took my bending moment on the wrong side of my diagram. So I had something like 400 kilonewton meters instead of 150 kilonewton meters because I took the compression instead of the tension side of the graph. With all my working out, I needed something like 6 and 36 bars in something that wasn't going to fit. I had 5 minutes to go. I realized what I had done, and I wrote a letter to the mistake. I have made this mistake. I'm fully aware I've made this mistake. And it just allowed her to know exactly what I had done, and I got carried through marks.
Knowing that you probably know wrong reasonably well, if you made one error at the start, that question's worth 20 marks, and all your processes were the same, how many marks could you expect?
So that little tiny thing there, say that's worth 1 mark, that's worth 1 mark. The rest of the process is fine, it's just because I can't time.
So you're expecting to be relatively
Yeah,
on the process, not
as you probably all aware with marks, sometimes it's not confusing. But when it comes to little things like that, that's not critical. You show you know what to do. That's a very slight math error. That's not even understanding of engineering, really. That's an understanding of can you make things in the calculator. That's not going to be critical. If you had calculated your shear capacity instead of your bending capacity in something, much more critical error. Because you clearly understanding that you don't have that understanding on your different sections. But that is the first of many mistakes in this exam. So again, this is the being to left side column. It's the same one I showed you before. Come up and take screenshots of these sketches. I can't send them to you. I've gone through these questions, so I won't go through it again. And then for our question C in this first part, exactly the same. As you will notice, he's even got the exact same weld size. Always a 12 millimeter, 12. Essentially, just copied and pasted.
So, like, do you know how you sometimes says like it could be a column to rafter one or a rafter to rafter? Then would this C question be for that connection calculated, or is it always just?
you put like every single bit of possible reinforcement on that sketch too. Like doublers, and you've also got the transverse stiffener and then compression and tension stiffness. And you just add everything to know that you like
Just add it. That's what I was told. Just add it all, because there's only 1 of 3 options. Make them into the exam.
What about instead of the transverse stiffener? Insane.
Just add a horn.
Just add a haunch. Yeah.
If you want to, it's a flat. In this one, there's no flat. You can add a haunch if you want. Nothing's stopping you. Might be a waste of time. This is the quickest one. Doing the exam. Sorry, I think it was like 2050.
Oh, we did that season.
Exactly. Organ upload connection. Exactly the same process that we followed. Previous exam, slightly different values because we've got a slightly different color. That's the only difference. I just use 40 millimeter. And in this case, I used 8 and 30s. So you can choose. Don't stress about, oh, they chose 30s and I chose 36s or they chose 24s. Just have a think about how things would line up in an actual section and make, so we've got 1000 WD. You're not going to be wanting to put it in 12s. You want something sturdy. So you'll be using something like M30s. In this, M36 is in this, just due to the sheer size of this member, I doubt that Bron will give you something. And if you notice, in this exam, I forgot to put in the minimum size. In 2018. Yeah. Then question two, once again, we're dealing with a water storage tank on an angle with a live load of 5 kPa, and we've got very similar but slightly different, quite annoying arrangement. This is the one that confused me on what side of the tank water is meant to be on, because it changes things. Don't stress. It's on this side. I think I did it on this side. So we go through, we calculate our capacity.
When you say at connection, where is that? You say the capacity is at connection. Which part of the diagram is the
And
connection?
that side looks enclosed, that you're like, oh.
So it's the connection between the stem and the base.
Yeah, so this gets a little bit, so it's gonna say can't wait.
So many times I've read
So she said the water is supposed to be on the right.
That's a big one, actually.
And you got the walker.
So we're calculating our capacity.
It's like,
Yeah. Pretty straightforward.
I did that the first time.
Calculating. Spacing. Go through and calculate. Phi and U, which we can get. And pretty easy. The most complex thing about this question is calculating the relevant moment. As you can see, I put the water on this side last year when I did this, but I have a feeling the water is actually on this side. Don't stress about that. It's not a critical assumption. Yes.
Can't you just take the waters on the side where the rebar is?
Yes, which is why I'm pretty sure that it's on the side.
Yeah.
However,
That's how I'm going to do this.
for some reason put it on the side when I did this question.
Looks like a tank on the left.
That was my fault. Looks like that logically looks like where the water should be. However, it's actually on the side.
Would you assume it goes all the way up?
Yeah.
Yeah.
Because I took it on the wrong side,
I mean, I'm just.
it can only go up.
Yeah.
Whereas it's actually up here.
but then on the left-hand side, is there just empty space there? Because he's doing like the soil of like.
Yeah.
It's all
Which is really
structures. It's
It's
like really unnecessary.
Yes.
That's why it's.
Yes. So like structurally, it's a lot more stable if the water's on the side.
Yeah.
That's why.
Yes.
Wait, so you just ignore that little triangle sliver of concrete between the F1 and F2? Between shapes 1 and F2, you don't have to worry about the concrete shapes having that little angle triangle.
Don't worry about it being exact. I just essentially do that with like a rectangle. Not this weird confusing thing. There's no point being really fiddly over things unless you know that you're gonna have time. It's what, a 2-hour exam. You're gonna be under time pressure. So probably the most confusing part about this is trying to work out all your moments and where it's coming about. So we have our forces of our concrete. I've broken it up into this stem part and walkway section. Our live load, which is our 5 kPa force of the walkway, our force of the water. In this case, we have the only thing that's unknown is the length of the walkway. And whereas in the previous question, it was the height that we know. We'll start that in. Again, it's easy. You have to split up your forces and you leave your arms separately. 3 and Pythagoras comes into this question annoyingly. I think it was just wrong trying to be confusing. Because I remember spending way too much time trying to work at geometry or anything. And then we calculate our length of our walkway, which in this case was 7.5 meters. And as you can see here, I have both 2009 and 2018 shear capacity formula. You guys don't know that's 2018.
We did 2009 as well in this on it.
Did he encourage
Yeah,
you
I
to
meant
do
to
it?
check both, but can we
This
just
is
pick
run
one
to
to do
like
it?
2000.
He's
Yeah, you want to
expressed
use
that
2009.
I wouldn't, if I've got to close down, you have to use the uni.
Not wrong.
But in your exams, use 2018, specify that you use 2018. Specify whatever, especially in those ones that have changed. But I expect you guys, you know how this is like field change, exchange, paper exchange. So then we're calculating our shear capacity. In this case, it just works, so we do not need any shear. 5 UC, greater than 5 ESA, and it acts as a slab. So, like, a question that says calculate the max shear force applied to the wall and check if the shear capacity of the wall is adequate. For a retaining wall, you essentially assume it to be a slab, which is when you only have to deal with ESA being less than 5 EC, whereas for beams and everything, you need it to be less than 5 EC. So therefore, we've got our capacity and it works in this case. And then thickness of the base. It's essentially the same thing as I went through in the previous question. We just need to make sure that the thickness is adequate to create a force or a cog. Calculate the development length. A1, A2, A3.
If he's drawn a hook or a cog, does that determine which one we should check?
So checking this 32 hasn't actually given you the remember size for this steel here.
Okay.
It will also have to recast the development plan for that. But you don't actually know what the steel size is, because if it's a, I don't know, 12 and 12, it's going to have a lot less development length than this M32 concrete or M32 member, so therefore it's going to be reliant on that. So essentially just make sure you're checking your thickness to the base to whatever's the larger one, and typically only gives that one kind of size anyway. That's essentially that question. The most confusing thing is calculating the forces on this structure. The rest of the question is always the same. Then, yep, okay, that is what I did last year. Great. So when we're dealing with this, it's really stable. We've got 2 hinges, so that means we've got no moment. This part, on this part. So all our moment is within this part of the section. Great. So because we've got a point load at this weird mid-span location, and we've got no moment in either of these columns, we're not going to have any vertical reaction or any horizontal reaction in either of these two supports, which you can see down over here, because otherwise that would induce some rotation in this part of the section. We also cannot have a vertical support on this support, a vertical reaction on this support, because that would induce a moment within this beam, which again we can't have. So essentially, we only have to deal with this part of the member, as these two members cannot have any shear load or any moment through them, axial force through them, because they've got no reaction forces within the support. So then when looking at this, we're going to have, and we've got no horizontal at this support either, so therefore there's going to be no horizontal reaction at this location, which means we're not going to have any moment induced within this column. So therefore all that moment is going to be essentially like that. You can see the red shape there. So we've only got any moment through that beam. Our axial forces are only through this top beam as well, because we've got no vertical or horizontal reactions through these three supports, which you can see by this orange. And then our axial supports, so we've got two vertical. Easiest way to deal with axial is find your reactions, so we've got two vertical reactions, and therefore they are both in compression. Does that make sense? Again, the best way to do these is to practice them and try to look at those locations and kind of easiest way to go through it. And then question 3, very, very similar to the 2020 exam I just went through, just got slightly different lengths and geometry. We're dealing with 140 mil thick slab. Self weight is 60 kilograms per meter for the beams, and we've already got a 4 kPa pipe load. And instead of 2.5 ton loads, we've got 2 ton loads. Again, go through and calculate your beautiful. This is another one where I've got errors. Where it says 6, it should say 3. For some reason, I took it as a full length here, where it's only half of the So again, don't use these values. This was going to check your answers are correct. So it's that 4 kPa times 3 meter to the free area. We should get 12 kilonewton meters. Our 2 ton point loads are 20 kilonewtons, and again with our 60 kilograms per meter is actually 0.6 kilonewtons per meter. Good job, mate. And then our concrete, again, that should say 3 instead of 6. But assuming that those values were right, we would have a 61 kilonewton per meter GDL distributed across these members. And so in this question, he's asking for C, which is these ones here. And in C, our length is 4 meters. Therefore, our shear value is 122 kilonewtons. And we would have, once again, like previous question, put opposing point loads at the same location, which gives us our D star of 182 kilonewtons. But that's wrong. It should be 182 kilonewtons. It will be approximately 100, just due to the errors in. And then for B, we're trying to calculate the capacity of A in the similar way that we did 2020. However, this time it's nice and symmetrical. So that max turning moment is actually in the center. So we've got C, D, and C. So we're assuming our one-way standing again, so there's no concrete load onto beam A itself. We have our point loads from now through things. Use the principle of superposition, which gives us a bending moment of approximately 1470 kilonewtons. And we apply our point loads at the center. That just is the max spending moment when you do the point loads in PR4. Then we are calculating our section capacity. So find what MS is approximately. So again, we're using that 1.5 to find that approximation between a member capacity and our section capacity. It is just an approximation of dividing by 1.5. It's not exact. It's just the easiest way to get a member size that will work. So in this case, I tried 1000 WD 215, which gives us our MS of 208,800. And again, if you have time, I know sometimes in these questions, it's time crunch, find your MB. So alpha S is calculated using this lovely formula, and in this case, it's 0.37. And alpha M is calculated using this formula here, which gives an alpha M of approximately 1.3. In this case, MB equals 1200 kilonewton meters. Now, as I was saying before, in the previous example where we had pre-chosen section that was adequate, in this case, we've chosen a section that's not adequate. Don't recalculate them unless you happen to have 10 minutes spare at the end of your exam. Just say 1000, the chosen section is not big enough, choose the next higher section and try again. Does that make sense? And then question C is exactly the same as it was in the previous exam. We're producing the exact same that help with the 2019 exams despite the mathematical errors that I can't math. Yes.
Just with the alpha M calculation there, so you've used that formula. In the code, there's like a few different ways to do it. So obviously we probably shouldn't just take it as one, but does it matter if we use that method or that table where it's got all these different notations you can do this?
That table essentially just approximates what is. So it gives you the table and it gives you this. Because in this case, we're using essentially 3 point loads. There's no case in the table that is similar.
Right.
That's why I've chosen to do it this way. If it was just a simple UDL, you can just use the ones in the table. If you don't have time to go through and calculate alpha M, assume it to be 1 and say this is conservative. No time, and then you can either write the formula or something if you don't have time to go through and actually calculate properly. It's unless it's a specific case in unless it's a very specific thing, this is more accurate than using the table unless it's one of the exact cases in the table.
I thought we could use like the one where there's a straight line and just do from like where you've got like M2 and M3 there. I thought that.
If that's the way you're comfortable doing it, yeah. There's plenty of ways to calculate alpha M.
Yeah.
It's just what's quickest in the time, and this is a pretty good way for me to work it out, especially when I'm dealing with three symmetrical.
Yeah.
Yeah. Does anyone have any other questions? I really don't like all the silence. Probably. Yeah. So 2017.
Yeah, it's gonna
The only major difference I want to point out in 2017 is these one of three things on angle. The question itself is pretty well the exact same. You've just got to actually find the length of these members because he hasn't given them to you.
I really wanted to say it was 3.
So you need to calculate the everything's a angle, but it's essentially the same as if it was square and then it's slightly larger.
So you just do
Nowhere near 3, but I want to call 3.
Yeah.
Essentially,
I probably do that.
everything is just slightly different geometry.
It just
Yeah.
By that, are your A and B lengths the same? They're like all 8 meters.
Yes, A and B are 8 meters.
It's C and D.
It's C and D.
I'll try. Confuse us.
Is there any, yeah.
So how did you get this formula for alpha?
Just give it in the code.
The M2 and M3 done.
M2 and M3 calculate them. So your M2 and M2 and M3 and
Well, the other one
M4. So M2 is first quarter, and M3 is your middle, M4.
Yeah, I was.
And yeah,
Slab
M2 and M3 are your.
That's gonna be you.
And then M4 is
Someone just wants
For work, that's all.
yeah, so in this one, they're equally spaced.
Right.
In the case that they weren't equally spaced, could you just make it like an
You're
overarching
looking at
symbol?
it from the top.
You just write down.
I think there's
It's kind of like bottom view, but like.
Oh, shut
If
up.
you have time,
It sounds like bottom view with extra steps.
making that aside.
I just remembered the David.
Where's that? Oh, it's not.
Let's study this. And like it's like, it's like, don't be like,
Yeah.
Yeah. So like, I think yes, it's not just for that too.
I know.
Quite ironic that last one is quite slow.
Coming back, being back. Like, give you bad feedback, I'm like,
But no, you know how it goes in scripture.
So I didn't.
Being so far along in engineering.
That seems so